So let's have a look at this. I'm going to show you this two ways. I'm going to show you this using Douglas bags, which is a technique that we use it to kind of teach physiology. And I'm going to show you using computerized system using breath by breath analysis. So let's start with the Douglas bag method. So if we just, here we go. So this is going to walk us through this protocol. So this is using open circuit spirometry. So what we've got a participant. We know their VO2 max. It's 66 mils per kilogram per minute. The power output at VO2 max, oops, pause it there, is 320 watts. That's really important. When they did a VO2 max test, they hit VO2 max at 320 watts. So remember, that's VO2 max is the ceiling for aerobic metabolism. Estimated VO2 at 120% VO2 max is 79 mils per kilogram per minute. So let's just go back just to remind ourselves. So remember that it was 66 mils per kilogram per minute at VO2 max. So 120%, which is what we're going to work at, times 66 will bring us in, as you'll see in a moment, at 79 mils per kilogram per minute. So we now know what our ceiling is. So remember, you can't have that. You can't have a VO2 in this individual of 79 mils per kilogram per minute. It's not possible. But that's the theoretical cost. The estimated power output at 120% VO2 max. Remember, 320 at VO2 max. The estimated power output at 120% VO2 max is 384 watts. So that's the power output they're going to work at. So here we go. So off we go. So now the test has started. So we're using Douglas bags to record the expired air. And so all we're doing here is taking 30-second collections into Douglas bags, and the participant is continuing breathing. So what's happening now is they're building a deficit. We've asked them to work at an intensity which is way above VO2 max. They're still trying to take oxygen in. You can see George's breathing. You can see the valve going up and down in the mouthpiece, in the filter. So he's trying to take the oxygen. He's building up a deficit. Viv is collecting the expired air into the Douglas bags. And we've got the Douglas bags all connected in series. And so what is happening is all George is doing is maintaining a constant cadence against that fixed resistance. Remember, that resistance is 120% of the resistance he was working at VO2 max. Okay, so notice you can just see his cadence is holding nice and steady, mid-80s. So he's just maintaining that cadence throughout. So we're just doing 30-second collections into these Douglas bags for the moment. So we move from that bag, we go into the next bag. So he's already done a minute. Okay, so we've done a minute collection. So we're now into the third bag. So now, of course, now what's happening is the anaerobic contribution is getting high. He's getting closer and closer to VO2 max. So he's struggling to get all the aerobic energy in. So now we're kind of just taxing anaerobic metabolism. So we're just pushing and pushing and pushing. The key to the test is you have to go to volitional exhaustion, because you've got to find out how big his capacity is to work anaerobically. So we're now onto the fourth bag. So we've gone a minute and a half. We're onto the fourth bag. Remember, these are 30-second collections. I apologise that my bit of camera's got in the way on the side here. I'm the most proficient at doing these kind of filmings. So he's holding on. Again, the key is just maintaining the cadence. Just got to hold the cadence all the way through. And he's gone. 2.5 minutes. So now I want to show you this slightly differently. So this is the same protocol, but using computer breath-by-breath based analysis. So everything is the same participant. So the background information is exactly the same. But what you'll see this time is you'll see the oxygen cost and the O2 and the CO2 at the onset of exercise, because we're going to measure it in real time. So everything is the same. So there's the participant. Okay, so now the data is being collected. So what you're seeing here is the blue trace is O2, the red trace is CO2, and so what you'll suddenly see is that the reason they're going backwards and forwards is just to do with the frame rate on the screen. But exactly the same thing is applying. So now, look, here we go. Now you can see the oxygen cost is increasing significantly. Okay, he's holding the cadence, so it's not like he's doing a different cadence, it's the fact is that he's trying to get the oxygen into the system. So we're now having to try and bring oxygen in to meet that demand, but it's never going to meet that demand. He's never ever, he's gone way beyond that blue horizontal line is what the computer thought his VO2 max was. He's way beyond that anyway, you know, he's way higher than what the computer thinks VO2 max is. But you'll notice that the CO2 levels are going really high. CO2 increases because you're working anaerobically. But notice that the O2 concentration, the rate of increase in the O2, can you notice it's starting to slow? It's starting to level out. He's hitting VO2 max, but the CO2 concentration continues to kind of rise. He's actually dropping off a little bit because he's not holding the cadence. And then he's blown. So what you had in real time, let's flip back to the lecture, is you could see the deficit being produced. So all we have to do is calculate the difference between the oxygen that theoretically would have been used at 120% VO2 max, take that, minus the oxygen that was used, and we get the anaerobic capacity. And in fact, Medbo goes on to write this, which is actually really neat. The accumulated oxygen deficit 1 reaches a maximum when the duration of the exhausting exercise exceeds 2 minutes. Miss a couple of points out. We come to point 5 here, and it is heavily dependent upon the exercise in muscle mass. Hence, it seems justified to conclude that the accumulated oxygen deficit provides a good estimate of the anaerobic capacity. The maximum accumulated oxygen deficit can be determined with a precision, now this is interesting, of 3 mils per kilogram. Now, you'll notice something. You think, normally we talk about mils per kilogram per minute. I'll come back to why minute's not there. Or 4% using individual relationships between the intensity and the O2 demand. To keep the methodological error as small as possible, the exercise should not last more than 3 minutes. The linear relationship can be extrapolated to some maximum intensities requiring large anaerobic release. We'll come back to this point in a moment. The reason that minutes isn't here is it's not a rate. It's not the rate at which you derive anaerobic energy, it's the capacity. So it's mils per kilogram. So they're kind of giving us the ground rules, okay? 2 minutes to 3 minutes. Fairly precise is what they're suggesting it can be. A lot of that depends upon the precision of your breath-by-breath system, and a lot of it depends on your precision perhaps if you're using Douglas bags. So here we can see what the data would look like. So in this example here, we've got each data point that you can see is breath-by-breath data. What I've done is I've fitted this pink line here. This is our kind of line that represents the trend for the VO2. So this is what happened in a test. Here's our exercise time. So the participant hit just about 2 minutes, so just about within the window that we wanted. Here's the oxygen cost in litres per minute. Now what I'm going to do is superimpose onto the top here, oops, what we estimated the oxygen cost theoretically would have been, in this case at 120% VO2 max. Remember, that's not possible. I can estimate it, but you can't take in more oxygen than you ever take in at VO2 max, but I can estimate it, right? I can predict it. And now add into that the deficit. So the deficit is these blue lines here. So it's the difference between what has been consumed and what theoretically would have been consumed. Now, remember that as soon as the participant starts to exercise, there is an instantaneous increase in the ATP turnover rate. And that ATP turnover rate it corresponds to the amount of ATP needed to exercise at 120% VO2 max, whatever that wattage is. It doesn't reflect the total amount of oxygen, it just reflects the amount of ATP. So what you can see is the top line is the oxygen demand, the bottom line, the pink line, is the oxygen cost. Oops. Therefore, the difference between the oxygen that theoretically would have been taken in and the amount of oxygen that has been taken in, so the total amount of oxygen that could have been consumed and the total amount of oxygen that was consumed, the difference between the two, according to this method, is the anaerobic capacity. But are there limitations? Well, we have to acknowledge that there are limitations to this as a method. It is not as robust as perhaps it first seems. Well, the first thing is this. You're making an awfully big assumption. Let me show you why. In order to estimate the workload for 120% VO2 max, you have to run a linear interpolation. You have to, and then extrapolate back to the x-axis. You have to create this line to work out what the intensity is for the MAOD trial. But this is based upon an assumption. You're making the assumption that there is a linear association between exercise intensity and oxygen consumption. Now, we're not going to cover this within this kind of module, but if you come and do the physiological profile from endurance module, you'll learn an awful lot more about this. But let me be clear, this relationship is not linear. It is linear up to what we call lactate turn point, and beyond that point we lose linearity. And of course, you're then assuming that that relationship exists beyond VO2 max, where in essence you can't take in any more oxygen than we hit at VO2 max. So how can we suggest it's linear? So that's the first limitation. Second limitation is associated with that, which is as you go beyond lactate turn point, because the oxygen cost becomes more variable and we lose the linearity, we can either over or underestimate the workload associated with whatever the percentages we want to work at of VO2 max. That therefore affects your calculation and estimation in the anaerobic capacity. And then really fundamentally, what's the test retest? Now we saw, did we not, in the constant load data that the authors were telling us, oh look, there's good correlations on the test retest. But we've been saying all along that test retest cannot be shown through correlation. So this is from Mike Doherty. It was published a number of years ago now. And I think it's a study that's actually not received as enough attention really. So what they've done here is they've done the MAOD twice in a group of participants. Now this is using limits of agreement. Now there's two fundamental points here. Remember that with limits of agreement, you have the x-axis, which is the mean across two trials. And in this case, it's the mean time across two trials for each participant. And on the y-axis, you have the difference in time between the two trials. So each of these points represents an association between the mean and the difference between those two trials. The middle line is the bias. It's not always at 0, but that's the bias. So that's the mean of the differences. So over the whole group, what's the mean of the differences? And then you've got the confidence intervals, which is the 95% confidence intervals, which are basically the standard deviation of differences multiplied by 1.96. But look at what they're showing you. Remember that the test typically has a duration of about 2 to 3 minutes. Okay? Look at what the variability is in exercise time. It goes from plus 35 to minus 35. There's near enough a 70-second variability on a test retest. 70 seconds. And because there is a 70-second variability, remember that nothing else has changed in this example. They're doing the same workload, everything is the same in the test retest. But because they have gone for a different amount of time across the two tests, guess what? The test retest for the actual anaerobic capacity is also significantly different. It goes from minus, what's that, about 15 mils per kilogram to plus, actually it's interesting, 15 mils per kilogram. So it's got a plus or minus 30 mils per kilogram. It's a big, big difference. It's a massive difference. So what Doherty's arguing is actually on a test retest basis, this test is flawed. Which is really disappointing, isn't it? Because actually, fundamentally, the philosophy behind it sounds very, very useful. there are a lot of things at play. I mean, here, there was no instruction given in terms of familiarisation for the participants and so on. So there's a lot of other factors here. But I think you have to recognise that a test that has only got a duration of 2 minutes and it's got around about 65 to 70 second variability over 2 minutes has got a lot of inherent issues. Its test retest is not there. We also know that we're able to separate the aerobic from the anaerobic, but you're not still able to account for the aerobic contribution that's coming from stored oxygen, which is from myoglobin. And so in fact what MedBo recommends is you do a correction factor to take into account the myoglobin stores. Now that's not uncommon because you can't measure directly, particularly using breath by breath or Douglas bags, you can't measure that contribution. So in 2011, I proposed an alternate method. This is what's called the all-out peak power test. It's a terrible name actually, but there's a degree of logic to this as a test. The all-out peak power test works on this assumption that you've got to take into account the high energy phosphates and glycolytic substrate metabolism and still be able to separate out the aerobic and the anaerobic metabolism. So there's a real logic to that. Everything else we've learnt seems to come into play. But what this test was trying to do was trying to eradicate the issues that were faced in the MAOD, which is test-retest reliability, but perhaps take advantage of some of their methodology. It can't be time limited for the reasons we've already justified. So here's what the test looks like. So again, in this test, what we do is we bring the participants in and we get them to do a test to volition exhaustion, a VO2 max test. We then bring them back in a subsequent visit and we basically put them on at a fixed workload. So it's a bit like doing a Wingate test that we've learned about in previous sessions. But in this test, what we do is we measure the oxygen consumption. So this line represents, the red line, the oxygen consumption during an all-out test. So you can see the oxygen consumption increases, then it just declines. And we keep them going, irrespective of whatever happens, until the oxygen consumption falls back to that which is achieved at VO2 max. But then what we also do is we record power output throughout the test. So what we've done is we've converted, this is the power output on the bike, and then this is for the oxygen consumption, we've converted the oxygen consumption back to the relative power output that was attained in the VO2 max test. So each of these goes back. So if they had whatever the power output was in the test, we convert it back into VO2. Sorry, VO2 was recorded in the test, we convert it back to the power output. And so what we have is two power lines. So this is the actual power in the test. This is the reflecting, in essence, the aerobic contribution. So the area between the two is our anaerobic capacity. And again, fundamentally, the test is terminated when the power output falls to VO2 max. And of course, you can see that the VO2 is being converted back to power, and we end up at the same point because this is VO2 max here. So what we've got is high energy phosphate contribution and a glycolytic contribution as well. The rationale is very good. The issue that we face is validity, because the only way we could validate this test at the time was we ran a correlation. We correlated it against a test we already know is shown to be unreliable, which is the MAOD. And actually, it got a really good correlation with it. But correlation, again, doesn't show causality, it shows association. But there are ways in which one could validate this test, which we've never been able to do. That would be, for example, using something like hypoxic chamber. So basically putting somebody in a situation where you reduce the amount of oxygen they're consuming. Therefore, if the test isn't affected by that, it therefore shows that the test is valid. What we have to do is show that there isn't a large aerobic contribution to the test.